Hello all. In my previous lecture, I discussed calculation of the total depletion width, calculation of the maximum electric field, and calculation of maximum electric field in terms of potential and total depletion width. Right? Now, in this class, I will start with biasing. Biasing. See, what is biasing? Biasing refers to applying an external DC voltage due to which the device can operate in a desired region. Right? For example, the PN junction can be biased in two ways. One is forward bias, another one is reverse bias. That means depends on your applied voltage, depends on our direction of the applied voltage actually. The PN junction can be operated in two modes. One is forward bias, another one is reverse bias. Right? Yeah, write down these points first. It refers to biasing, it refers to applying an external DC voltage, due to which the device can operate in desired region. Desired region. Right. Next point. The PN junction can be operated in two modes. The PN junction can be operated in two modes. The first one is forward bias. Second one, reverse bias. Right. Now, I will start with forward bias, the first one. Forward bias. Yeah. Copy this diagram. Right. So now all of you completed? Right. So now all of you see first why it is named as forward bias. Actually, the battery positive potential is given to the positive terminal of PN junction and the battery negative potential is given to the negative terminal of PN junction. Then this PN junction is said to be in which bias? Actually, forward bias. Right? See, when the forward voltage increases, okay, what happen actually? The barrier potential is decreases or it becomes smaller. Actually, without applying any voltage, actually, what will be the barrier potential? The barrier potential is V0. Already we derived. Already we calculated, right? This is the barrier potential actually, without applying any voltage or unbiased condition. After applying some voltage, actually, what happened to the barrier potential? Actually, the barrier potential is decreases in case of forward bias, right? Why it is decreased? See all of you. See this. What is the direction of the barrier potential in case of unbiased condition? This is right. This is all our acceptors. These are all our donors, right? Okay. And what is our applied voltage direction? Actually, positive to negative. See, our applied voltage is oppositely to the existing barrier potential. That means what will be the net barrier potential? Actually, the net barrier potential is decreases or it becomes smaller, and it is given by VB equal to V0 minus V. See, V0 minus V means the net barrier potential is decreases, right? Right on. When the forward voltage is increases, then the barrier potential is decreases. Or it becomes smaller. And it is given by VB equal to V0 minus V. VB equal to V0 minus V. right? Where VB is the net barrier potential. VB is the net barrier potential. Next, V0 is the built-in potential. V0 is the built-in potential, and V is the applied external voltage. Applied external voltage, right? Yeah, next, so all of you, see, due to the small barrier potential, actually, the majority charge carriers are easily moving from P to N and N to P. Actually, what are the majority charge carriers actually in P? Holes, and in N actually electrons. The majority charge carriers are easily moving from P to N and N to P, and it can produce a net current in the direction of P to N. In the direction of P to N, okay, that current is called as what actually? That current is called as forward current, right? You know, this forward current is due to two mechanisms actually. One is drift mechanism, another one is diffusion mechanism. In case of forward bias actually, the forward current is due to both drift as well as diffusion. So where is the drift current is can flows, and where is the diffusion current can flows actually? You know, the drift current can flows at the far end of PN junction. Already I told what is drift actually. The current flows due to applied external voltage, right? Okay. So that means the drift current can flows at the far end of PN junction. And where is the diffusion current flows actually? The diffusion current can flows actually at the junction, because here there is a concentration gradient, right? That's why the diffusion current can flows, right? Yeah. Copy. Write down. Write down. Due to the small barrier potential, due to small barrier potential, the majority charge carriers can easily moving from P to N and N to P. P to N and N to P, and produce a net current in the direction of P to N. In the direction of P to N. Yeah, underline in the direction of P to N. Yeah, this current is called as forward current. This current is called as forward current. Yeah, underline the forward current. Next point, the forward current is due to both drift and diffusion. Right, underline drift and diffusion. Next point, the drift current can flows at the far end of PN junction, Next, diffusion current can flows at the junction. Yeah, underline drift current flows at the far end of PN junction, and diffusion current flows at the junction, right? Yeah. Next, so see, due to the positive potential of battery actually, so the holes are drifted toward the junction. So if the holes are drifted toward the junction and it can produce a current, that current is called as what actually? IPP of X. IPP of X is nothing but hole current in p-type semiconductor. You know, this IPP of X can start decreases as moving toward the junction. Why it decrease as moving toward the junction actually? Due to recombination, right? See, when the hole is moving toward the junction actually, in the meanwhile the electron will appear, because in p-type majority are holes and the minority are electrons. When the hole is moving toward the junction actually, so in the meanwhile electron will appear. Whenever the hole is seeing an electron, what happens? It will recombine and disappear. Due to which this IPP of X starts decreases, right? This IPP of X start decreases. Okay, at the junction, you know, IPP of X start decreases. Just a minute. Just a minute. Right. Yeah. Next, IPP of X star decreases. At the junction, there is a concentration gradient. At the junction, there is a concentration gradient. Due to this concentration gradient, actually, what happened? Due to this concentration gradient, the holes will diffuses into N side. The holes will diffuses into N side, and it can produce a current. That current is nothing but what actually IPN of X. You know, this IPN of X can become zero. This IPN of X can become almost negligible actually, due to what? A recombination. Whenever the holes will enter into N side, right, all holes will recombine with an electrons. Then this IPN of X can become almost negligible. Yeah. Similarly, due to the negative potential of battery, okay, the electrons are drifted toward the junction. That is INN of X. Okay, and it produces a current, that is INN of X. That means electron current in entire semiconductor. You know, this INN of X can start decreases as moving toward the junction. Yeah. Why it will decrease? Actually, due to recombination. Again, at the junction, there is a concentration gradient or concentration change. Due to this concentration gradient or concentration change, what happens? These electrons will diffuse into P side, right? And produce a current. That current is nothing but what actually? INP of X. You know, this INP of X is almost negligible due to what? Recombination. That means, what is the conclusion actually? See, when the PN junction is operated in forward bias, what is the dominating current across the PN junction actually? The dominating current across the PN junction is diffusion current, and the drift current is almost negligible. But what I told previously, the forward current is due to both drift plus diffusion. Actually, both mechanisms are involving, but which one is dominating actually? The dominating one is diffusion, right? Yeah, copy. Write down. Due to positive potential of battery, holes are drifted toward the junction. And produce a current IPP of X. Yeah. Underline IPP of X. Right. Next point. This IPP of X can start decreases. As moving towards the junction. Due to recombination. Right. Underline recombination. Also underline the drift, the word drift. Right. Next point. Due to concentration gradient at the junction. The holes will diffuse into N side. And produce a current IPN of X. Yeah, underline a word of diffusion, also underline IPN of X. Right. Next point. This IPN of X become negligible at the far end of N side. At the far end of N side. right? Next point, due to negative potential of battery, next point, similarly, comma, due to negative potential of battery, electrons are drifted towards the junction, and produce a current, INN of X. Right, underline INN of X. Next point, INN of X can start decreases as moving toward the junction, due to recombination. Right, next point, due to concentration gradient at the junction, electrons will diffuse into P side, and produce a current, INP of X. Right, next point, this INP of X become negligible. At the far end of P side. At the far end of P side. Right, due to recombination. Right, next conclusion heading. Conclusion. When the PN junction is operated in forward bias, the dominating current across the PN junction is diffusion current. Yeah, this is the conclusion. Right, now write down a question in your classroom workbook, question number 2. Question number 2. Right, write down a question. In a forward biased PN junction diode, the sequence of events that best describes the mechanism of current flow is option A injection and subsequent diffusion and recombination of minority carriers. Yeah, next one, option B injection and subsequent drift and generation of minority carriers. Next, option C extraction and subsequent diffusion subsequent diffusion and generation of minority carriers. Generation of minority carriers. Next, option D. Option D. Extraction. Next, extraction and subsequent drift. Subsequent drift and recombination of the minority carriers. Recombination of the minority carriers. Right. So which one is the right option actually? Option A is the right option. Injection and subsequent diffusion and recombination of the minority carriers. Actually, see here, injection means what actually? What? Drift. See, due to the positive potential of battery, the holes are drifted. Drifted means here injection is happening. Right? Okay. When the holes are moving toward the junction, what happen actually? They will recombine. The few holes will be recombined. Means it will recombine with the minority carriers. Right? Next, at the junction, due to the concentration gradient, what happen actually? What happen? The holes will diffuse into N side. That means here the diffusion is happened. See, the forward current is due to because of the three mechanisms. Injection is nothing but drift, recombination of minority carriers and diffusion. That means which one is the right option? Option A is the right option. Injection, subsequent diffusion and recombination of the minority carriers. Right? And the next topic, reverse bias. Next heading, reverse bias. Yeah, copy this figure. Right. See, what is the reverse bias actually? Reverse bias is nothing but the battery negative potential is given to the positive terminal of PN junction and the battery positive potential is given to the negative terminal of PN junction. Then this PN junction is said to be in which bias? Reverse bias. Right? See, when the reverse voltage is increased, what happened? When the reverse voltage is increased, what happened actually? Depletion region is increases. Right? If depletion region increases means what about the barrier potential actually? The barrier potential also increases. What is that net barrier potential actually? The net barrier potential is nothing but VB equal to V0 plus V. See, in case of forward bias actually this is V0 minus V, but in case of reverse bias V0 plus V. How? See this, the direction of the built-in potential actually this is negative and positive. And see our applied voltage direction actually this is negative and positive, right? That means our applied voltage and existing barrier potential direction is both will be in the same. That means what will be the net barrier potential? Increased, right? Here due to this large barrier potential, actually no majority charge carriers will flow from P to N as well as N to P. That means what will be the majority carrier current? Zero. Right? But minority carriers will flow from P to N and N to P because of high reverse voltage. What happened actually? Minority carriers will flow from P to N and N to P due to this voltage actually, and it can produce a current in the direction of N to P. See, in case of reverse bias, what will be the direction actually? N to P. Okay, and which is constant and negligible actually. Why it is negligible? Because the current is due to minority, right? So that current is called as what actually? That current is called as reverse saturation current or leakage current, right? That is denoted with I naught, right? Yeah. Copy. Write down the notes. When the reverse voltage is increases, when the reverse voltage is increases, then depletion region is increased. Depletion region is increased, and also barrier potential is increases, and also barrier potential is increases, and it is given by VB equal to V naught plus V. VB equal to V naught plus V. Right. Next point. Due to the large barrier potential, the majority charge carriers will not move from P to N and to P. Majority charge carriers will not move from P to N and N to P. Due to which majority carrier current become zero. Majority carrier current become zero. Right. Next point. But few minority charge carriers will move from P to N and N to P. And produce a current in the direction of N to P. Underline in the direction of N to P, right? Which is constant and negligible. Constant and negligible. This current is called as reverse saturation current or leakage current. Reverse saturation current or leakage current. Right. Underline reverse saturation current or leakage current. Right. Yeah. Next, put the heading observation. Right. Yeah. See what you observed. See, in case of forward bias, actually the dominating current is what actually diffusion current, and the drift current almost negligible, right? What about reverse bias actually, right? See, in case of reverse bias, actually there is no chance of diffusion because of large barrier, means because of a large depletion region actually, right? This depletion region can prevent the diffusion process. That means only which mechanism is involving? Drift mechanism is involving, right? That means only the drift current will flow, the diffusion current will be zero. Diffusion current is zero, right? Right on. When the PN junction is in reverse bias, operated in reverse bias, then drift current can flows. And diffusion current becomes zero. And next heading, conclusion. Next heading, conclusion. Conclusion. Right. Now see the conclusion actually here. See here, what is a PN junction actually? The PN junction is nothing but is a two-terminal device. PN junction is nothing but is a two-terminal device actually, okay, which allows the current in one direction. Allows the current in one direction means in case of forward bias actually it will allows the current, right? And oppose the current in another direction. Oppose the current in another direction means in case of reverse bias actually there is no current. Current almost negligible. Okay, am I correct or not? Right. Similarly, what is a diode actually? Diode is nothing but it is also diode. Diode means di means two nodes, right? Diode also a two-terminal device which allows the current in one direction and oppose the current in another direction. That means what is the conclusion? Simply the PN junction acts as a PN diode. PN junction acts as a PN diode, right? Right on the first point, right on the conclusion, first point. PN junction is a two-terminal device. PN junction is a two-terminal device which allows the current in one direction, and oppose the current in another direction. Oppose the current in another direction. Yeah. Next, second one. Diode is a two-terminal device. Diode is a two-terminal device which allows the current in one direction, and oppose the current in another direction. Oppose the current in another direction. Third one. Third point. Hence, the PN junction acts as a PN diode. Hence, the PN junction acts as a PN diode. PN junction acts as a PN diode. Right. See here, now I am going to draw the symbol of a PN diode actually. See here, graphically. So what is a PN diode actually? A diode means two terminals. One is anode, another one is cathode, right? So which allows the current in one direction, right? Which allows the current in one direction means how to represent direction graphically? Arrow, right? Arrow. You know, this arrow indicates the forward current, right? And oppose the current in another direction means how to indicate like this, right? This is the symbol of a PN diode, right? Copy this one also. Right. Next heading, note. Note. Right. Listen. What is the note actually? See, for an abrupt PN junction, I already discussed what is abrupt, right? Abrupt means sudden change. For an abrupt PN junction actually, what is the relation between depletion width and applied voltage actually? See, for an abrupt PN junction actually, WB is proportional to square root of VB. Square root of VB actually. So this is in case of biased condition. In case of unbiased condition actually this VB become V0. In case of biased condition actually this VB become this V0 become VB, right? Actually this VB is V0 plus V in case of reverse bias, and in case of forward bias actually this is V0 minus V, right? Next, similarly for a linear PN junction. In case of linear PN junction actually what is the relation actually? The WB is proportional to cube root of VB. Cube root of VB. Actually we have two types of junctions actually, abrupt and linear actually. Okay. Linear PN junction is nothing but the junction at which the concentration is minimum and the concentration is maximum at the far end of p-n junction. Such a p-n junctions are called as what actually? Linear p-n junctions actually. In case of linear p-n junctions, okay, the relation between depletion width and the potential is cube root of VB. In case of abrupt, square root of VB, right? Copy? Yeah, copy now? Yeah, next write down a question in classroom workbook, question number 3. In classroom workbook, question number 3. Right. Write down. An abrupt p-n junction has a built-in potential of zero point 0.7 volts, 0.7 volts, and has a depletion width of 2 micrometer, 2 micrometer at a reverse bias of 1.3 volts, 1.3 volts. If the reverse voltage is increases to 7.3 volts, then depletion width will be right. All of you read the question once actually. What is the given data? The given right abroad p-n junction. They given a abroad p-n junction actually. Also they given what actually? They given a built-in potential. Built-in potential of how much? 0.7 volts. Right. Also they given a depletion width how much? 2 micrometer when the reverse voltage is 1.2 volts. Sorry, 1.3 volts. If this reverse voltage is increases to 7.3 volts, then the depletion width will be right. This is we want to calculate. Right. What is the relation between width and voltage actually? That is W is proportional to under root of VB in case of abrupt. Right. Now this can be written as W1 by W2 is equal to under root of VB1 by VB2, where VB1 is V0 plus V1 and V0 plus V2 in reverse bias condition. For example, if it is a forward bias, it will become what actually V0 minus V0 minus, right? Now what is the W1 actually? W1 is nothing but 2 micrometer by W2 equal to, this is 0.7 plus 1.3, this is 0.7 plus 7.3, then W2 is how much? 4 micrometer. This is the depletion width value when the reverse voltage is increases to 7.3 volts, right? Copy. Completed? Next topic, IV characteristics of a PN diode. IV characteristics of a PN diode, right? See why we can call as IV not VI, right? You know, in case of P and diode, what is happening actually? We are applying some voltage, so current is flowing. That means input is voltage and output is current. Generally, output is on y-axis and input on x-axis, right? That's why it called as I versus V characteristics of a P N diode, right? So here I want to draw the IV characteristics of a P N diode actually. Yeah. For drawing characteristics here, I start with forward bias first. I start with forward bias, right? So first in forward bias, applied voltage is 0. In forward bias actually applied voltage is equal to 0. Then what will be the current through the diode and what is the voltage across the diode actually? Both will be 0. Current through the diode is 0 and voltage across the diode also 0. Next, if this applied voltage is increases to small amount, very small amount, then what is the current through the diode actually? Still 0. Right? Why current through the diode is still 0 even though if you apply a small amount of voltage actually? Because this applied voltage is used to cancellation of the barrier voltage. That's why the current through the diode is still 0. Next, if the applied voltage is increases further, what happens? If the applied voltage is increases further, what happens actually? The current through the diode is suddenly increases. Why it is suddenly increases actually? Due to cancellation of the barrier, right? Now see, I am drawing the characteristics actually. If applied voltage equal to 0 means both current through the diode and voltage across the diode will be 0. If applied voltage is increases by a small amount, actually, what will be the current through the diode actually? Still 0, right? If applied voltage is increases further, then what is the current actually? The current is suddenly increases due to cancellation of barrier, right? This is the IV characteristics of a PN diode in forward bias, right? Yeah. First copy. Right. Write down notes. First, heading forward bias. Heading forward bias. When applied voltage is equal to 0, then both current through the diode and voltage across the diode is 0. Both current through the diode and voltage across the diode is 0. Right. Next point. When applied voltage is increases by small amount. When applied voltage is increases by a small amount, then current through the diode still 0, because this applied voltage is used to cancellation of barrier. Next, when the applied voltage is increases further, then the current through the diode suddenly increases. Due to cancellation of barrier. Due to cancellation of barrier. right? Yeah. Yeah, next, soon all of you. Next, I can define a cutting voltage actually. Actually, this V gamma is nothing but cutting voltage. Okay. What is cutting voltage actually? Cutting voltage is nothing but the applied voltage at which the diode starts conducting. The applied voltage at which the diode starts conducting is called as what actually? Cutting voltage. You know, in case of PN junction, this cutting voltage will depends on what actually? This cutting voltage will depends on the built-in potential. Okay. Again, this built-in potential depends on what actually? Intrinsic concentration. Very important point. Okay. Now for silicon PN diode actually, what will be the cutting voltage actually? The cutting voltage is nothing but 0.7, and for germanium, what will be the cutting voltage actually? The cutting voltage is nothing but 0.3. Right? Here, why germanium has low cutting voltage than silicon? Because it has high intrinsic concentration. It has high intrinsic concentration. It has high intrinsic concentration means it has low built-in potential, right? See how low built-in potential actually, we know V naught equal to what? V naught is nothing but Vt into ln of Na into Nd by Ni square. Already we derived in my previous lecture. Calculation of the built-in potential, right? See, germanium has high intrinsic concentration means it has low built-in potential. It has low built-in potential means it has low cutting voltage. That's why germanium has low cutting voltage than silicon. Right? Right down. Right down. The applied voltage at which the diode starts conduct is called as cutting voltage. Is called as cutting voltage in bracket V gamma. Right. Next point. The cutting voltage depends on built-in potential, which in turn depends on intrinsic concentration. Right. Underline the statement. Cutting voltage depends on built-in potential, which in turn depends on intrinsic concentration. Yeah. Next one. Copy this one. For silicon, V gamma is 0.7. For germanium, V gamma is 0.3. Right. Right on. Germanium has low cutting voltage. Than silicon. Because it has high intrinsic concentration. Right. This one also important statement. Underline. Germanium has low cutting voltage than silicon because it has high intrinsic concentration. Right. Now coming to reverse bias. Just reverse bias means interchange the battery potentials. Right. See a reverse bias actually. See, in case of reverse bias, what happens when the reverse voltage is increased? See, already we discussed when the reverse voltage is increases, what happen actually? The depletion region is increases. If depletion region increases means what about the barrier potential increases? Barrier potential increases means no majority charge carriers will flow from P to N and N to P, right? No majority charge carriers will not flow, but the minority carriers will flow from P to N and N to P, okay? And it can produce a constant and negligible current, right? So this current is called as what actually? Reverse saturation current. See here, current almost constant, also negligible almost. Constant and negligible current. That current is nothing but I naught, right? You know this for silicon material actually this reverse saturation current is an order of nanoampere, And for germanium, the reverse saturation current is an order of microampere, right? Here, why germanium has high reverse saturation current than silicon? Because it has high intrinsic concentration, right? In case of germanium, the intrinsic concentration value is 2.5 into 10 power 13, and whereas in silicon, the intrinsic concentration value is 1.5 into 10 power 10, right? So it has high intrinsic concentration. High intrinsic concentration means it has high reverse saturation current, because reverse saturation current will depends on what? Intrinsic concentration actually, right? Copy? Write on the points. Write on the points. When the diode is operated in reverse bias, when the diode is operated in reverse bias, right, the current through the diode is constant and negligible. Constant and negligible. Constant and negligible. Right. This current is called as reverse saturation current or leakage current. Reverse saturation current or leakage current. Leakage current. Right. Yeah, copy this one. Also copy this characteristics, reverse characteristics, and also copy this diagram. Yeah, write down note. Write in the note. Germanium has high reverse saturation current. Germanium has high reverse saturation current than silicon because it has high intrinsic concentration. It has high intrinsic concentration. It has high intrinsic concentration. Intrinsic concentration, right? Yeah. Thank you. To be continued in next lecture.